In our last lesson, we talked about the different types of chemical bonds, ionic and covalent. And what we learned is that chemical bonds involve the electrons. Ionic bonding, we transfer electrons. Covalent bonding, we share electrons. So in this lesson, we're going to focus on the electrons and how they're involved in a chemical bond. So a little bit of a review. Chemical bonding is when elements are going to come together to form a compound, and that chemical bond involves the electrons. So let's review how we figure out electrons in an atom. So if we have a neutral atom, we know that the number of protons should equal the number of electrons. And so we can just use the atomic number. So if we look at lithium, which is down here, lithium is number 3 on our periodic table. So we have an atomic number of 3. And we know if it's a neutral atom, it should have the same number of protons and electrons. So it would also have 3 total electrons. Nitrogen, look for nitrogen on our periodic table. Nitrogen has 7 for its atomic number. And if it was neutral, it's going to also have 7 electrons. And finally, sodium, atomic number is 11. It would have a total of 11 electrons. So how are those electrons arranged around our atom? So electrons are found in energy levels. So energy level 1 is closest to the nucleus, shown in the picture here. So shell 1. Energy level 2 is a little bit farther out, and energy level 3 is even farther. Now each of those energy levels can hold a certain number of electrons. So in our first energy level, we can only hold 2 electrons. The second energy level, we can hold up to 8. Our third energy level, we can hold up to 18. Now, you probably won't be asked for questions higher than that, but energy level 4 can hold up to 32 electrons. Energy level 5 can hold up to 50, and energy level 6 can hold up to 72. So let's practice drawing in our electrons for these 3 atoms. So we figured out in our warm-up how many electrons total they should have. So we said lithium should have 3, nitrogen should have 7, sodium should have 11. So let's place in our electrons. So in our first energy level, we can hold 2 electrons. So I'm just going to use dots for my electrons. You could use an E if you want. So I can put 2. That means my third one has to go in energy level 2. So 2 in the first, 1 in the second. Let's try nitrogen. So I have to show 7 electrons for nitrogen. So I'm going to put 2 in the first. So that leaves me with 5 more. Remember, the second level can hold up to 8. So those 5 can all fit in the second energy level. So 2, 3, 4, and 5. So 7 altogether. Sodium has to have 11. So I can put 2 in the first. That means I can put up to 8 more in the second energy level. So that doesn't quite take care of all of them. So I can put 10, show 10 of them. So I can put 8 more. So that's 10 electrons, and that leaves me 1 more has to go in the third energy level. So this would be my electron diagram, or the Bohr model diagram, for these 3 atoms. Now, it can be kind of tedious drawing out each of these diagrams, putting in your dots. So we write something called an electron configuration to simplify showing where the electrons are located. So the 1 in front, of all these, so the big numbers out front, like the 1 and the 2 for lithium and carbon, that is telling you the energy level. So what ring around the nucleus is the electron found? S is called an orbital. It's just telling you the shape. We're not going to really worry about that. And the 2 up above, so the superscripted numbers, the little numbers up top, those tell you how many electrons are found there. So for chlorine, its electron configuration is 1s2. So in the first energy level, has 2 electrons. And then 2s, 1. So in the second energy level has 1 electron, just like we drew in our last example. Just simplifies it a little bit. And then the S tells you the shape of the cloud. So really remember, these aren't really rings or orbitals. There are these clouds where electrons could possibly be. So an S shape is spherical. A P shape kind of looks like dumbbells. And then D and F have varying shapes as well. So another example here is carbon. So in the first energy level with an S-shaped cloud has 2 electrons. The second energy level with an S-shaped cloud has 2 more. And then again in the S second energy level, just a little bit different shape, has 2 more electrons. So 2 in the first energy level, 4 electrons in the second energy level. So how do we know what numbers and letters to put? So you want this reference sheet. This is going to tell you how to do your electron configurations. So we always start up at the top corner at hydrogen. So we always start up here at this one. So we know it's labeled 1s, 1. And then we go across to 1s, 2. We're just going to keep working our way down and across, just like you're reading a book, till you get to the element you need to draw the configuration for. So let's try an example. Let's try sulfur here. We already had carbon. So we want to find sulfur on our periodic table, on our little reference cheat sheet here. So here's sulfur way down here. So again, we're going to start at the top. So we start at a 1s. And there's 1 box, 2 boxes labeled 1s. So it'll be a 1s, 2. Then we're going to go down to the next line. So here we see it's called 2s. And there's 2 boxes labeled 2s. So 2s, 2. Then we're going to go across. This one's called 2p. And let's count how many boxes. So there's 1, 2, 3, 4, 5, 6. So 2p, 6. So we're going to keep going until we get to sulfur's box. So we're going to go down to the next row. So this one's called a 3s. And there are 2 boxes labeled 3s. So 3s2. Then we're going to go across. This one's called 3p. And we're going to count how many boxes till we get to sulfur. We're going to stop at sulfur. So there's 1, 2, 3, 4, and we're at sulfur. So this would be the electron configuration for sulfur. So our first energy level, we have 2 electrons. Our second energy level, we have 8. So 2 electrons total, 8 electrons total, so 2 and 6. And then our third energy levels, we have 4 plus 2, so we have 6 electrons. Let's try another one. Let's look for fluorine. So fluorine is here on my chart. So again, I'm going to start at the top. So it's called a 1s, and there are 2 boxes labeled 1s. So 1s2. Sorry, that looks a little off. Then we go down to 2s. So 2s, and there are 2 boxes labeled that. Then we're going to go across. We see 2p. And there are 1, 2, 3, 4, 5 boxes labeled 2p. So this would be our configuration for fluorine. 1s2, 2s2, 2p5. So our first energy level, we have 2 electrons. Our second energy level, we have 5 plus 2, we have 7 electrons. So let's try a couple more examples. So sometimes our configurations can get quite long, right? If we were to try to do mercury, we're all the way down here. So we'd have to write all of this till we get to mercury. So a way we can do a shortcut is by starting at one of the noble gases here. Remember, noble gases is this last column on our periodic table. So if we wanted to write the configuration for mercury, instead of starting up at the top at hydrogen, we could start at the noble gas that comes before mercury. So the noble gas that comes before mercury would be xenon. So to show that we're starting at xenon, we put it in brackets, so xenon. And then we could just continue our configuration. So after xenon comes a 6s. So 6s, and there are 2 boxes. Now you have to remember here we have to insert this row. So 4f would be next, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 can fit there. And then we can go back up to the 5D, and there are 10 boxes to get to Mercury. So you have to remember 4F goes here before you can do the 5D, and then before you can do the 6D, the 5F get inserted there. That's there to remind you. Let's try argon. So if we wanted to do argon, we can start at the noble gas that comes before argon. So we can do the shortcut and we can start at neon. So I'm going to put neon in brackets and then continue my configuration. So I'm going to go to a 3s, and there are 2 boxes. And then I'm going to go across to a 3p, and there are 1, 2, 3, 4, 5, 6 to get to argon. So this would be my configuration for argon. So you can use the shortcut method if it helps. You can start at one of these noble gases. Or if you don't like the shortcut method, you can always start at hydrogen and work your way across and down until you get to the right element. That's how we write configurations. So how do we know this is what they actually look like? How do we know there are 2 electrons in a 1s energy level, or 5 electrons in the next energy level? So we measure these with something called an electroscope, and we're going to I'll demonstrate this for you in class. So we can use an instrument called a spectroscope. We can take our atoms, we can pump some electricity into it, and the electrons get excited and they get bumped up to a higher energy level. And when they come back down, they give off that extra energy as light. And we get these spectrum, these light beams in this picture down below, these bright lines that appear. And these lines appear at certain energies. And these energies are associated with the energy level the electrons are found at. And no 2 atoms would have the same spectrum, same combination of lines. So it's kind of like a fingerprint for an element. So we can look at hydrogen or helium. Here's a spectrum for helium. Here's a spectrum for zinc or sulfur. And it's their unique fingerprint. So this is how we measure what elements are found in stars in outer space. We can use a spectroscope that's really high powered. We can measure the light coming off of that. And we can get these bright line spectrums. And we can know what elements make up the sun or the different stars in our solar system. So let's kind of move a little bit back to bonding. Remember, we were talking about the electrons are involved in the bond. But what electrons? We do our electron configuration. We have like the 1s2, the 2s2, the 2p6. Which of those electrons are involved in a bond? And it's not all of them. It's only the valence electrons. These are the electrons that are in the outermost ring, or the highest energy level. And that's because they're farthest away from the nucleus, so they're more easily to get loose from an atom. So on your periodic table, I want you to add these. So in our first column, all of these atoms have 1 valence electron. So add this to your periodic table. The second column, they always have 2. Boron's column, they always have 3, 4, 5, 6, 7, and 8 as you go across the groups. Don't worry about the transition metals. We're going to kind of ignore them. They don't really behave. The maximum number of valence electrons that something can have is 8. And remember, this relates back to our octet rule. Stable things have 8 electrons. So these valence electrons are what are involved in a chemical bond. Let's kind of put this all together. So how do we show these valence electrons? So we draw something called a dot structure, symbols showing the number of valence electrons something has. So like lithium is in column 1, has 1 valence electron, so it has 1 dot around itself. Beryllium's in column 2, so it has 2 valence electrons, or 2 dots around it. Now if you notice, we always put 1 dot per side, and if we have to, we can double up. So like nitrogen needs to show 5. So we put 1, 2, 3, 4 dots around it, and one of them will have a pair. So let's try an example. So sodium, if we look on our periodic table, sodium has the symbol Na. It should have a total of 11 electrons, but out of those 11, because it's in the first column, means it only has 1 of those 11 are valence electrons. So its dot diagram would be Na with 1 dot. Now, how many bonds can it form? So unpaired dots mean it can form a bond. So because sodium has 1 unpaired dot, meaning it needs a partner yet, it can form 1 bond. Let's look at carbon. Carbon has a symbol of C on our periodic table. Let's look back. Carbon is number 6, and 4 of those electrons are valence electrons. So 6 electrons total, 4 of them, because it's in column we labeled number 4, has 4 valence electrons. So carbon needs to have 4 dots. Remember, we're going to put 1 per side and not double up if we don't have to. So carbon can form 1, 2, 3, 4, has 4 unpaired electrons. So it can form 4 bonds. Magnesium has the symbol Mg. If you look back on our periodic table, magnesium is number 12, and it's in the second column. So it has 12 total electrons. 2 of those are valence electrons. So our dot diagram would be Mg, 2 dots around it. Don't double up unless we have to. So it has 2 unpaired electrons, so it can form 2 bonds. Let's look at aluminum. So aluminum is number 13, and it's in column we labeled 3. So aluminum Al has 13 total electrons. 3 of those 13 are valence electrons. So our symbol is Al, and we want to show 3 dots around it, 1 per side. So it has 3 unpaired ones. It can form 3 bonds. And lastly, let's look at neon. Neon is number 10. It should have 8 of those being valence electrons. So neon Ne, total electrons we said were 10. Out of those 10, 8 of them are our valence electrons. We need 8 are in the outermost energy level. So we have our symbol. We need to show 8 electrons. So don't double up yet. So 4. And we have to double up to show 8. So if we look at neon, how many unpaired electrons does it have? So all of them have a pair. So neon does not form any bonds. That's why it's a noble gas.